Welcome to Sairam Educational Channel. In this video, we will be going to learn about electrochemistry, part 1, class 12. Let us go into the chapter. Introduction. As you all aware that electrochemistry is a branch of chemistry which deals with the conversion of chemical energy to electrical energy. At the same time, which also deals with the conversion of electrical energy to the chemical energy. So in this particular case, if you can see, a very vast number of metals and some of the chemicals are being produced by use of electricity, and so here we will be using electricity to make some chemical reactions. So these are called electrochemistry. It comes under the electrochemistry, and those are called as electrochemical process, like electrodeposition, electroplating. There are different ways electrochemical synthesis. Similarly, we can also using electricity from a storage units like batteries, where there is a chemical reaction happens and gives the electricity. Fuel cells, where there is a chemical reaction and output is electricity, which we will be using for different other applications. So here the conversion of chemical energy to electrical energy is happening. In the previous case, the conversion of electrical energy to the chemical energy, like reactions. At the same time, as we know that our all sensory organs works based on signals from different parts to the brain to different parts, and it was found to be that they are all electrochemical in origin, nature. So all the signals works based on electrochemical potential. So if you can see, electrochemistry is a vast subject and it is interdisciplinary in nature. So we will try to learn more about this. First we will see the electrochemical cells, where a spontaneous redox reaction gives rise to electrical energy. You see, the reaction is spontaneous. It happens on its own when you bring them in contact. For example, if you can see here there is one beaker was taken. In this beaker there is a solution which containing zinc sulfate or zinc chloride, mostly zinc sulfate, zinc 2 plus ions, and there is a metal rod, zinc rod. So zinc rod is dipped in zinc sulfate solution, at the same time copper rod dipped in the copper sulfate solution. These both are externally connected through a conductive wire, like copper wire, any electrical conductor wire. At the same time, to have a contact between these two solutions, there is an internal salt bridge which acts as a conductor for the ions. So ionic movement happens through this salt bridge. Electrons movement happens through the external wire. As soon as you connect this setup, there is a production of potential that is around 1.1 volts from this. If you can connect to over here voltmeter, it reads around 1.1 volt. What happens here? This is the redox reaction happens in this particular cell. This redox reaction is a combination of two off reactions. If you can see, zinc is converted into zinc 2 plus, where it undergone oxidation by losing 2 electrons at the left side of this particular vessel. Similarly, copper 2 plus ions in this solution took 2 electrons externally, which transferred from the zinc rod to here and converted into copper. These two off reactions together makes this particular reaction. So what happened generally? All the time the zinc loses 2 electrons and become zinc 2 plus. Those ions are dissolved in the solution went into the solution. Those two electrons which stays on the zinc electrode, since electrons are more here, they will be moving through the external circuit to the copper rod, where this copper 2 plus ions takes those two electrons and reduces to copper. So there is a continuous movement of electrons from the zinc electrode to the copper electrode. As you know that the flow of electrons is nothing but current. So the current will be in the opposite direction of the flow of electrons. Flow of electrons happens from this side to this side, so the current will be in the opposite direction. So there is a production of current. And the voltage difference between these two electrodes, as soon as you connect, you will get around 1.1 volts. This particular cell is electrochemical cell, which is specially named as, this particular example, zinc and copper cell, is called Daniell cell. So this device is also called as, these type of devices are called as galvanic device, galvanic cell, or voltaic cell. In that particular cell of this type is called Daniell cell, that is zinc copper. But these are all called electrochemical cells, or that this is called galvanic cell or voltaic cell. So the total reaction is a combination of these particular two reactions. Copper 2 plus 2 electrons, it taken 2 electrons, so it is electrons are consumed, so it is called a reduction reaction. Where electrons are produced, it is called oxidation reaction, so it is the reduction of cell reaction. This is the oxidation of cell reaction. Together is our cell reaction. This cell reaction is the one which is having the chemical energy which gives out in the form of electrical energy. The delta G of this reaction will leads to the conversion of electrical energy. So a potential difference is develops between the electrode and the electrolyte, which is called the electrode potential. If you can see previous case, so what happened? We dipped zinc rod in a zinc sulfate solution. Similarly, solution. When we dip the zinc rod in the zinc sulfate solution at the electrode electrolyte interface, that means at the metal rod and the solution interface, there is a tendency of zinc from the zinc rod tries to lose electrons and goes into the ions zinc 2 plus. At the same time, there is also a tendency the zinc 2 plus ions which present in the solution gains two electrons and deposits as zinc atoms on the zinc rod. So there is a two-way reactions happens, trying to happen. One is zinc try to dissolve as zinc 2 plus and loses two electrons. At the same time, zinc 2 plus ions gains those two electrons and converts into zinc. So these two reactions happens. Because of these two reactions, there is a potential difference. There is a charge separation happens at the electrode and electrolyte interface, the junction between electrode and electrolyte, where the metal and solution contacts are there. There is a charge separation creates. This charge separation leads to the potential. That particular potential is called as electrode potential. So a potential difference develops between the electrode and the electrolyte. In our case, zinc and zinc 2 plus solution, or copper 2 plus solution, which is called as the electrode potential. When the concentrations of all the species, in this particular case, I have a zinc rod. If the zinc rod is a purely zinc, 100% zinc, and the solution zinc 2 plus ions, zinc 2 plus ions concentration is 1 unity, then the electrode potential generated at that electrode electrolyte interface is called as standard electrode potential. It is called as standard electrode potential. As per the IUPAC nomenclature, International Union of Pure and Applied Chemists, they have the convention. They generally convention in the, as per that, standard reduction potentials are now called as standard electrode potentials. So whatever we consider as standard electrode potentials, remember that they are all the standard reduction potentials. So in a galvanic cell, the half cell in which oxidation takes place is called anode, and it has a negative potential with respect to the solution. So we have seen in the previous case where zinc tries to lose electrons and become zinc 2 plus. So zinc becoming zinc 2 plus. So this is called oxidation. So now the zinc electrode is called as anode, because where the half cell in which oxidation takes place is called anode. Once a zinc metal loses 2 electrons and going to zinc 2 plus, and those 2 plus ions are dissolved in the solution, then those 2 electrons stays back on the zinc. So the zinc rod gets now negative charge. More number of electrons negative charge. So that is negative potential with respect to the solution. Similarly, if you can consider the second half reaction where the copper, what happened? Copper 2 plus ions reduced to copper metal. So when they are reducing, they takes the electrons from the copper rod, that is the metallic copper. From the metallic copper, those copper 2 plus ions which are in the solution takes the electrons. So the now metal is having less number of electrons. So it becomes positive charge. So it is a positive potential with respect to the solution. And the process happened is reduction. So now the copper electrode is called as cathode. So these are the naming we use for these electrochemical cells. One need to remember that. So how we represent these electrochemical cells or galvanic cells? Before representation, we will see another concept is called, I have two electrodes. We have seen one is the anode, another is the cathode. There is a potential generated at the anode, that is a potential of anode and cathode potential. When I connect these two, there is a potential difference happens between these two electrodes of the particular galvanic cell. That is called cell potential and is measured in volts. Volts is the unit for potential. So the cell potential is nothing but the potential difference between these two of electrodes of a galvanic cell. I hope you are understanding. The cell potential is the difference of reduction potentials of the cathode and anode. You see, here when you are measuring a cell potential, remember that you consider the reduction potentials of both cathode and anode. I agree that at the anode there is oxidation. The potential what we get is oxidation potential. But when you want to calculate the cell potential, you have to take the reduction potential of the anode. That is, it should be opposite, nothing else. So the reduction potentials, you take the reduction potentials of cathode, you take the reduction potential of anode. Now you subtract these two, that is called your cell potential. It is also called as electromotive force of the cell, that is cell electromotive force, EMF of the cell. EMF will be measured when there is no current is drawn through the cell. While representing galvanic cell, you need to remember that you have to keep the anode on the left hand side and cathode on the right hand side. When you write a cell on a paper, you have to first write the anode part, then the cathode part. Cathode should be on the right side. So generally the galvanic cell is represented by placing a vertical line between metal and electrolyte solution. You see, when I write a anode, for example in the previous Daniel cell case, my anode is zinc 2 plus. Zinc is the metal, you write the zinc first. For example, if you take a copper example, it is like that. If it is zinc means first you write zinc, then zinc 2 plus. Here it is a copper electrode we took. So copper solid rod dipped in copper 2 plus aqueous solution. There is an interface between electrode and electrolyte. This interface is represented by using a vertical line. Metal and electrode. Similarly, there is another electrode, right side, there is a cathode. Cathode, what are the ions? Silver plus ions. It is a reduction. So silver plus ions are there in which solution? Aqueous solution, in water based solution. And there is a silver rod dipped into it, that is solid. So Ag plus Ag, this is the cathode and this is the anode. So each electrode is represented where I have two phases. One is solid phase and liquid phase. Here also liquid and solid phase. The phases are separated by using vertical lines in both the electrode, and these two electrodes together is called the galvanic cell. So these two are internally connected by using a salt bridge that is represented by double vertical lines. Now this is a complete galvanic cell. Here the anode is copper electrode, here the cathode is silver electrode. Cathode was kept on the right side, anode was kept on the left side. Now the cell potential. As I already told, each one, when I dip a metal rod in a metal ion solution, obviously there is a electrode potential difference creates at this boundary. That is called electrode potential of anode. Similarly, here also there is a electrode potential generates. That is the electrode potential of cathode. So the difference between these two is called as cell potential. I told cell potential generally we will consider as reduction potential. So now you take the reduction potential of reduction of cell, that is the cathode, that is E right minus E left. That is the reduction potential of cathode minus reduction potential of anode. Remember all these potential, whatever we are mentioning, whether it is cathode potential or anode potential, you need to consider it as a reduction potentials when you are calculating cell potential using this particular equation. E cell equal to E right, that is E cathode, minus E left, it is E anode. For example, here you can see copper copper 2 plus and silver plus silver. Similar example. Half cell reactions, you know, copper is the anode. Here anode oxidation, copper solid metal converts to copper 2 plus by losing 2 electrons, so it is oxidation. Similarly at the cathode there is a reduction undergoes, silver plus ions takes the electrons, each ion take 1 electron, so 2 electrons and becomes silver. The overall reaction is this: copper, these two can be added left hand side and right hand side can be added, electrons will be cancelled out both the sides. So now you have copper solid plus 2 silver ions give rise to copper 2 plus silver. Now the cell reaction, E cell equal to E right minus left, E left. E right is the E silver silver and right left is E copper 2 plus copper. This is the way one need to calculate the cell potential. Very important, lot of problems comes based on this. Now we will once again see our electrochemical cell. You see this is the cell we have seen previously. Zinc sulfate solution in which zinc rod is kept. Copper sulfate solution in which copper electrode is dipped, immersed, and both are connected externally by using a copper wire or any wire, conductive wire, and here we kept a voltmeter or a whatever it is to measure whether the flow of electrons are there or not. And there is internal connection was done by using salt bridge, where some ions salt will be embedded in gel. Now this is the cell. As soon as when I connect like this, I will get a 1.1 volts potential. That means there is a spontaneous chemical reaction is happening. Because of that spontaneous chemical reaction, there is a movement of electrons. Once the movement of electrons is there in the circuit, that's called as current. Now we will try to apply external voltage to this cell. Now what I did, instead of happening this, I connected this to another external battery. This is a battery. This E external, this is external potential. Now the external potential I am applying, but the applied potential is less than the cell generating potential. I told because of the spontaneous chemical reaction, there is a potential generation that is around 1.1 volt in this particular cell. Now I applied a external voltage to this cell, but that external voltage is less than 1.1. So if this is the case, when you are applying external voltage 1.1 volt less than 1.1 volt, then what will happen? The reaction whatever previously happened, they will continue. There is no alteration. Correct? What are the previously happened? Zinc loses 2 electrons and goes into zinc 2 plus ions, and those electrons move externally from zinc electrode to the copper electrode, and copper 2 plus ions takes those 2 electrons and deposits as copper. Same electrons flow from zinc rod to copper rod, and hence current moves from copper rod to zinc rod, and continuously zinc dissolving and copper is metal is depositing. Correct? If another case, if you consider, if I applied the external voltage which is exactly equivalent to 1.1 volts, then nothing happens because both the reactions are opposing. When no flow of electrons happen, because I am trying, the non-spontaneous reaction happening here is trying to send the electrons this direction, zinc to copper, but the actional voltage is trying to send the electrons from copper to zinc. You can see the signature signs here. So what will happen at this particular case? There is no current, emitter deflection is 0. Here emitter deflection is there, but here there is no deflection, I equal to 0. No chemical reaction happens, zinc will not dissolve, copper 2 plus will not deposit, both will not happen. But if you consider the third case, where my actional voltage is greater than 1.1 volts, what will happen? Once the actional voltage is greater than 1.1 volt, we are forcing electrons to the system. When the electrons are forcing, what will happen? Electrons flow stops from zinc to copper and now starts from copper to zinc. So electrons flow from copper to zinc and current flows from zinc to copper. Zinc is deposited at the zinc electrode. Previously it was dissolved from the zinc electrode and copper was deposited previously. Now copper dissolves at the copper. That means equivalent opposite reaction is happening. This particular concept where I am using actional current and opposite reaction is happening, non-spontaneous reaction. Spontaneous reaction is previously zinc dissolves and goes into zinc 2 plus, but now it is happening reverse, zinc is depositing. That is a non-spontaneous reaction, but we made it to happen, that particular reaction, by providing actional voltage where electrical energy was used to generate chemical reactions. That particular is called as electrolytic cells. Those cells are called as electrolytic cells. So electrolytic cell is a device which uses electrical energy to carry non-spontaneous chemical reactions. Now we will see how to measure these electrode potentials. I already told that when you dip a metallic rod, a conductor, in its solution, ion solution, then there is a interface. At the interface, there is a tendency of the metal trying to move into metal ions. At the same time, metal ions takes the electrons and convert to the metal. Because of this tendency, there is a charge separation happens at the metal and the solution interface, and which creates a potential. Then how do you measure these electrode potential? We can measure only the difference between these two. The potential of individual half cell can't be measured, remember. If I have to measure a potential by using a voltmeter, I need to have two signals. One is this electrode, another should be something else. So that's why a single electrode potential can't be measured. That is, half cell cannot be measured. But what we can do? We can measure only the difference between two half cell potentials. That gives the EMF of the cell. That is the EMF of the cell. For example, you take a cell in which you have two half cells, measure the EMF of the cell and consider one half cell potential difference is 0, arbitrarily 0. Then the measured EMF of the cell is the electrode potential of the another electrode. Clear? So this is the way we need to calculate. So we are taking some half cells called standard hydrogen. For example, a standard hydrogen electrode. These are standard electrodes where their potential we arbitrarily fix as 0. Standard hydrogen electrode was made and its potential was considered or arbitrarily fixed as 0. This is the electrode representation, of cell electrode representation. There is a platinum metal solid on which hydrogen gas was adsorbed and which was dipped in H plus solution, that is acidic solution. This is the way electrode is made. And its potential is 0 at all temperatures. Whatever you consider the temperature, its potential. You can see this is the way the construction of the standard hydrogen electrode happens. You take a beaker in which you have the acidic solution, that is the concentration of H plus ions. You can consider as 1 molar generally taken, standard 1 molar solution of H plus ions, in which you take a wire, metallic wire like platinum. At the end you put a platinum plate, small plate, you see. Over the platinum plate you coat a platinum. Should be like finely divided nano platinum coating. Then it is called as platinum black because it absorbs light, it will not emit any light. so it becomes black in color. So it is a finely divided platinum coated on a platinum foil. That means very nano size platinum particles are coated on a platinum plate that now acts as our electrode, and which can be sealed in a glass tube in which you can able to pump your hydrogen gas at 1 bar pressure. Then what will happen? This hydrogen gas goes like this and it is absorbed on the platinum metal. Now that will be dipped into the H plus solution. Generally, this is a simple electrode of H2 gas in H plus. But how to have contact between a gas and solution? That's why this gas is being adsorbed on the metal surface, that is platinum surface. Once you adsorb and dip it and continuously pump the H2 gas at 1 bar pressure, if the H2 gas is at 1 bar pressure standard and the solution concentration is 1 molar, then this electrode is called a standard hydrogen electrode and its potential was considered as 0. What could be the electrode reaction? Then there should be electrode reaction like our zinc 2 plus gives 2 electrons, zinc becomes zinc 2 plus and 2 electrons, like copper 2 plus takes 2 electrons copper. Similarly here H plus ions from the aqueous solution takes the electrons and becomes half H2 gas. And the standard hydrogen electrode consists of platinum electrode coated with a platinum black, as we already discussed. How we can do it? Remember, whenever you want to measure electrode potential of a particular electrode, you need to connect that electrode on the right side as a cathode, and the standard hydrogen electrode should be connected on the left side. Remember this notation is very important. We are trying to measure the redox potentials of electrodes. I told standard electrode potentials means these are the redox potentials. So if you want to measure the standard electrode potential of a particular metal and metal ions, then you connect that electrode as the cathode and this electrode as the anode. Then take the difference between these two electrodes, that is cell EMF. That EMF is the electrode potential of copper, because this potential was considered as arbitrarily 0, hydrogen electrode potential. So now you see the standard electrode potential, that is cell potential, EMF of the cell. This symbol represents standard potential. All are standard reduction potentials. Whether I say or not, these are all standard reduction potential. So the standard electrode potential is nothing but E right minus E left. So E right is the copper electrode potential, E left is obviously 0. So whatever the measured potential, this is the measured potential. By using voltmeter you can measure. That is equivalent to ER. That is the right side electrode potential. That is the copper electrode potential. This is the way one can calculate standard electrode potentials of several couples, metal ions or non-metals, everything. So now in this particular case, the measured potential is around 0.34 volts, which is the standard electrode potential of copper 2 plus copper. There is another thing also we should learn here. These are all very, very important for your examination point of view. You see here the standard electrode potential of copper 2 plus copper electrode is positive, 0.34 volts. What it means? The positive potential indicates that copper 2 plus ion gets reduced more easily. That means the reduction of copper 2 plus to copper happens more easily than H plus converting to H2 gas. Clear? Understood? So copper, when I dip in acid solutions like HCl, remember that copper will not get oxidized in HCl solution. It will not dissolve. Because when copper metal comes contact with H plus ion solution, what is the reaction it happens? Copper 2 plus gets into copper, but not copper to copper 2 plus. Because copper 2 plus ions gets reduced more easily, the potential is positive. The opposite reaction will not happen, that is copper will not dissolve as copper 2 plus in this HCl solution. That's why in acids, you learned in 10th class that whenever metals dip in acids, evolve hydrogen gas. How it happens? This is because of these reactions. But in this particular case, it will not happen. If I take a zinc, then it happens. We will show that. But copper case, it will not evolve hydrogen gas, remember. Clear? Because copper 2 planes trying to get reduced to copper, rather copper oxidizing to copper 2 plus and releasing H plus ions, leading to the H plus ions conversion to H2 gas. That never happens. But if you take another example, for example, this is hydrogen electrode, once again standard hydrogen electrode or normal hydrogen electrode, NH or SHE, and this is zinc electrode. You see the cell potential is around minus 0.76 volts, and that is the standard reaction potential of zinc 2 plus to zinc. Here you see the potential is negative. Once the potential is negative, it is easy that zinc converts into zinc 2 plus ions. That means oxidation happens. That means in another way, other way, we can also tell that zinc 2 plus ions gets reduced very difficultly than H plus ion. That means H plus ions gets reduced to H2 gas than zinc 2 plus to zinc. That means when I put zinc metal in acid, immediately we will see the hydrogen gas bubbles. That means H plus ions easily gets reduced to H2 gas. At the same time, what happens? Zinc will be dissolving. Zinc dissolves as zinc 2 plus ions. So this is the important thing one need to understand. Go through once again these slides such that you will be understand. Now we seen the EMF Daniell cell, as we told the starting onward, zinc to zinc 2 plus, copper 2 plus to copper. This is the Daniell cell, and you have a left electrode is the anode where oxidation occurs, and its potential by using the previous way we can calculate the potential is minus 0.76 volts. Sorry, V, and copper 2 plus to copper the potential is 0.34 volts. Now I have two off cells, both are connected in Daniell cell, and both off cells potentials I know, so it is easy to calculate the cell potential, Daniell cell potential. EMF of the cell equal to E0 cell, that is E right minus E left. Which is the right electrode in this case? Copper is the right electrode. Reduction happens, so its potential is 0.34 volts minus minus, and what is the left side electrode? That is anode, E right left, that is minus 0.76. So plus 0.34 minus of minus 0.76 together is 1.1 volts. This is the EMF of the Daniell cell. You see, there are some electrodes, they will not participate into the electrode reactions, like platinum metals and gold metals. Those are called inert electrodes. The metal itself will not participate into the chemical reaction, like zinc is dissolving zinc 2 plus, copper 2 plus will go and deposit on copper metal. They are directly involving in the chemical reactions. But these are the metals, platinum, gold, similar metals will not directly involve in the chemical reactions, but the reactions can occur on their surfaces. Like in the standard hydrogen electrode, where platinum does not directly involve into the reactions, but H plus ions are getting reduced and deposited. H2 gas produces H2 gas. That H2 gas will be absorbed on the platinum surface. Correct? So those are called as inert electrodes. Inert, they are not participating in reactions. Inert means non-active. They do not participate in the reaction but provide the surface for both the reactions, oxidation or reduction reactions. Like platinum in the previous case, hydrogen electrode, platinum acts as similarly, and bromine electrode case where platinum similarly act as inert electrodes. So this is the slide with which we will stop this one. You see, what is the use of these standard electrode potentials? They are very important in our chemical reactions to understand them. These are the tables represents shows the standard electrode potentials at 298 Kelvin. All were considered in aqueous medium, remember? If you can see in the table, the topmost is F2. F2 gas takes 2 electrons and converts to to F minus, and the potential standard reduction potential is 2.87 volt. So from there it starts and goes down up to minus 3.05 volts, where lithium plus ion takes electrons and converts to lithium. So in this case, you also having a hydrogen where its potential is 0, is it not? You can find out the hydrogen, its potential is 0 here. H plus takes 2 electrons and H2 gas. So if you can see, these are all the oxidizing agents. They all act as oxidizing agent this side. This right side acts as reducing agent. So these right side, reaction right side, all these are called as reduced forms. These are all called as oxidized forms because a oxidized form takes the electrons and reduces. This is the redox reaction, is it not? So the oxidized forms takes the corresponding electrons and converts to its corresponding reduced form. So these are all the one, they are all reduced form. So they are all reducing agents. These are all called oxidizing agents. If you can see, the oxidizing agent strength is more for the topmost cases. F2 is more oxidizing power than other case like cobalt, H2O. If you can tell, hydrogen peroxide is oxidizing agent, fluorine is also oxidizing. Out of these two, if you want to compare, fluorine is the more oxidizing than hydrogen peroxide. That means it is easily reducing. It is easily reducing. What is oxidizing agent? The compound which accepts electrons is called oxidizing agent. The oxidizing agent himself or itself is reduces. Who is able to reduce easily, that is called oxidizing, because it consumes electron. The electrons were taken from someone else, so it is oxidizing the other. So this F2 is oxidizing agent because it is easily reducing. Its potential is positive. Previously we seen if the positive potential is there, it easily reduces. So this is the best oxidizing agents. So lithium plus is very weak oxidizing agent. F2 is a strong oxidizing. Similarly, the F minus ion, fluoride ion, is very weak reducing agent. These are all reducing agents, remember. So if you can consider F minus is very weak reducing agent, but lithium is very strong reducing agent. That means it easily loses electron, lithium. Lithium easily losing electron means it is oxidizing, opposite, reverse, you can see. Lithium trying to lose electron and goes to lithium plus. It means it is trying to lose electron, means it is giving electron to someone else who can take the electron. That means they are reducing. So that's why lithium is a reducing agent, best reducing agent. Is it not? So you know that all the alkali metals, sodium, potassium, lithium, all these trying to lose electrons easily. They prefer to be in their ionic state rather their metallic state. That means they are trying to lose electrons. They are losing electrons means they are getting oxidized. That means they are better reducing agents. So all the alkali metals comes down here, you can see. So these are the better reducing agents, and top is the least reducing agents. So the lithium plus, all the time lithium metal tries to be in lithium plus state. Its potential is more negative. It is very difficult to reduce lithium to ion to lithium because its potential is very negative. So remember, whenever the standard electrode potential is more negative, that reduced form is a highly high strength reducing agent. It is a strong reducing agent. And its oxidized form is weak oxidizing agent. Clear? And so reduced form is more stable. So now I have two things. One is oxidized form. Another way we can also try to understand using this with respect to the hydrogen, because hydrogen is a standard. We have it zero potential. So who are having above hydrogen in this table, they are all having positive potential. Their reduced form is more stable compared to hydrogen gas. You remember? Hydrogen electrode, the hydrogen gas is the reduced form. In another case, all these are the reduced forms. So what we are telling, if the potential is positive, that is above your hydrogen electrode, then those reduced forms, all these right side, F minus, cobalt 3 plus, water, gold, are more stable compared to your hydrogen gas. That means these metals, when you dip in acids, they will not produce hydrogen gas, remember. They will not produce hydrogen gas. They will not get oxidized. They will not get oxidized. They are trying to reduce easily. They will not get oxidized. That means they will be converting into left to right. All reductions are happening. If you take silver and put in HCl, nothing happens. There is no production of hydrogen gas. Gold, you see, all these metals are here. Similarly, on the other hand, if you can understand, those are below the hydrogen, they are all having negative potentials, and here hydrogen gas is more stable than their reduced forms. That means when I put iron in acid, immediately hydrogen gas produces because that is more stable than these iron. That means iron easily gets oxidizes and it converts into Fe2 plus or Fe3 plus. Chromium, lead. So all these, when you dip in gases, acid solutions, immediately they produces hydrogen gas. That means hydrogen gas is more stable than the reduced form when the potentials are more negative.